right? So we're connected to computer audio, so it's all good. Unfortunately, there are two of me for some reason. So it looks like it signed me in twice, which is okay, not a problem. Closed, there we go. And then we do a screen share. That's two. There we go. And I can tell that it's recording because this little thing here. Actually, if I go here, I can go to recording and it's already recording, so I'm not gonna. So we're good here. We're good here. All right. And I don't like the zoom because it takes up the entire top bar. So when I need to click on the app itself, I have to be clicking on just this portion and not the entire portion of the top bar. All right, so let's go back to the homework assignment. And one thing I do want to kind of point out is not so much I'm asking you guys to tell me what the answer is, but I want you to think about it. So when you turn in the homework assignment, when you turn in the quote unquote quiz, what was on your mind? Okay, did you think that, yeah, I think I did okay in this test. I think I'm gonna get pretty much all of them right, maybe one accidentally wrong. Or did you think that, oh, this is not gonna be good? Okay, I'm definitely not getting all of the concepts. And then compare that to the actual outcome of the assessment. So there are four possibilities, right? Because there's your expected outcome, good versus bad, and then the actual outcome, which is good versus bad. So the good is fine. The bad is not actually bad either, because you have this gnawing feeling that I'm not quite getting it, okay? So that's actually good, not a problem. So it's the one in the middle that is interesting. You think you got it, but the outcome did not reflect that. That is the one that we need to address, okay? Because that means the person who is experiencing this is not self-detecting that the concepts were not understood. And that would be the one that I'm most concerned about, because the other one, which means, I think I totally flunked this test, but it turned out to be okay. That can be a confidence issue, that can be, how that person is self-assessing. It's like, oh, I think I'm totally flunking this one, but it turns out to be okay. So that's not a knowledge issue. It's not a learning issue. It's more of a self-confidence issue. That person just needs to kind of let it sink in and accept that I'm actually capable in that case. All right. So I just want to bring that up because I think it is important for us to self-evaluate and be able to tell whether I did it right or not. All right. So what I'll do is I'm going to do the test just the same way that you do. All right. So this is question number 1. Set A, uppercase A, has elements A, lowercase ab, and B has lowercase abc. The question is asking which of the following is true. So when you answer these questions, there are 2 ways to do it. You can always just confirm the correct answer, or you can rule out the wrong ones, okay? So we can do both. In this case, B is a subset of A is not true, because in order for B to be a subset of A, everything in B needs to be in A. And in this case, well, C is in B, but not in A. So the first choice cannot be the right answer. The second one is A is an element of B. Well, it is not that a set cannot be an element of another element of another set, excuse me, but it really has to do with, oh, that's it. That's my Discord, thing, doing this thing, and let me just kind of turn it off. Because I subscribe to, I think this one came from the Computer Science Club of ARC, because they did not turn off that auto welcome feature. All right, there we go. That distraction is gone. All right, so the second one is not true because A is a set. It is not like a set cannot be an element of another set, but in this case, do we see any element of B being a set by itself? The answer is no. So that means that the second choice is also going to not the right choice. Yes.
So to make it an element, you would put brackets around the A and the B in the set B.
Right. So if I have extra, brace here and also here, then this would have been true. Yeah. All right, so let's look at the third one. A is a subset of B. So now the question is, what makes a set a subset of another set? It means in this case, everything in A needs to be found in B, which is the case. Okay, so I am tentative to answer C as the right answer. So unless I'm running out of time, I want to evaluate the last one too, just in case that I missed something earlier. Okay, so I'm going to evaluate the last one, which is B is an element of A. B is a set. Okay, it's it's a pretty big set with 3 elements. It is not because B is a set that it cannot be an element of A. It is because in A, we do not have anything in A that is a set. So, it cannot possibly be the last one. The last one cannot be true. So the only choice that I have left here is C. Do we have any questions about question number 1? Okay. Huh? An element in a set is basically a value that is a member of that set. A membership. Because a set is a container. So you can look at a set like a bag, okay? And you can look at anything to be a potential element. So I'm going to pick something that is not originally in my bag. So look at this dry board marker, and you can always ask the question of, is the dry board marker in the bag? Okay, if it is, then it is an element of the set. And if it is not, then you say it is not an element of the set. Or you can say this dry board marker is an element of this bag. It's false, because element of is basically an operator. It returns a value that is either true or false. You have to give me a solid, concrete example. So you have to show me a set, you show me a value, then I can tell you whether that thing is an element of the set is true or not. So it is much more helpful if you just give me a concrete example. Can you do that? I mean, if you can, I mean, I can answer the question. No. So, okay, so I'm not really sure how to answer that question, because I can boil down the concepts or the symbols to a certain level, and element containment or membership of a set is something that I really can't explain any further. I can use an analogy of a file in a folder. Okay, you can check whether a file is in a certain folder or not, right? So in this case, the file is the element or potential element, and then the folder is the set. It's about membership. Okay, is this thing a member of that collection? That is the question. So in this case, A is an element of this particular set. B is an element of this particular set. 20 is not. Okay, 20 is not an element of A. 20 is not an element of B, because according to the notations here, 20 is not a part of either set. Are we okay with that concept? No? Yes? No? All right, so you can come to my office hour and we can, I can see if I can explain that any further. All right, question number 2. Okay, let me see if I can show the entire question. All right, so question number 2 is kind of a fun question because it has all of these possible choices and you have to check all the right ones. All right, so in this case, you're given a constraint. Okay, so I want to kind of mention the term of a way of thinking, a logical way of approaching a question is look at it as constraints. Okay, I give you a constraint. What is the constraint? The constraint is when you look at the union between set A and set B, the union must have exactly A, B, C, D, E as its elements. And on top of that, in this case, the and is a conjunction, which means we want the other one to also be a part of the constraint. That constraint says A minus B, or the difference between A and B, is the set that only has C and E in it. So that means, C and E should only be found in A, but not in B. Okay, that's based on the definition of the set difference operator. So both of those are constraints. It doesn't tell you anything about, so what exactly is A and what exactly is B. It just tells you that if I apply the union operator, this is what I'm supposed to get. If I apply the difference operator, that is what I'm supposed to get. So now you need to go through each and every single one of these and find out, if A is ACE and B is ADB, does it meet all of these requirements? All right, so you're basically doing a filtering thing. And in this case, the answer is, yep, that meets all the requirements, because in order for A, B, C, D, E to be the union of A and B, should be found in at least one of A or B. Can be both, but it has to be at least one. So we can find that A is in uppercase A, B is found in uppercase B, C is found in uppercase A, D is found in uppercase B, E is found in uppercase A. So it meets the first requirement already. The second requirement says A must contain C and E, and B cannot contain C and E. So in this case, A does contain C and E, and B does not contain C and E. So it is now also meeting the second requirement. So as a result, it is a part of the answer. So I'm just going to go through this really quickly. In this case, it is yes, okay, because CE is in A but not in B. But when you look at the union of the two sets, then you get A, B, C, D, E. This one cannot be the right answer because A is empty to begin with. So we basically automatically know that there's nothing in A that cannot be found in B because A itself is empty. There's nothing in A to begin with. And then this one is not correct either, because we want C and E to be in A, but not in B. But you can see that in B, there's also C and E lowercase. So this is not the right answer. This one is not the right answer because we want C and E to be found in A, but not in B. That's not the case. This one is not the right answer because A, B, C, D, E is found in A and B at the same time. So the difference between A, B, C, between uppercase A and uppercase B would have been an empty set because there's nothing that we can find in A that is not found in B. If we look at this one, it is checked, okay? Because, we can find C and E over here and not found in B, but when you look at the union, we get everything. And in this one, it's also not checked because, D and E are found in A, but not in B, but so are A, B, and D. But the requirement here says we should only have C and E being found in A, but not in B. So the last one is not, is not applicable. It is not part of the answer. So do we have any questions about number 2? You mean this one? Well, you mean this one? Down to this one? Well, this one cannot be a part of the answer because in order for A minus B to be C and E, C and E can only be found in A, but not in B. The second one, you mean this one?
Yeah.
So this one is the correct answer because, if I look at A, B, C, D, E, it can be found in at least one or the other set. Okay, because A can be found in B, B can be found in B, C can be found in A, D can be found in B, and then E can be found in A. So it meets the requirement of the union, but it's also meeting the requirement of the difference because A contains C and E, but B does not.
Okay.
All right, thank you. So moving on to question number 3. choose the correct answer, whether it's true or not, okay? So A is an element of, okay, this is why you're where in the English description is really not easy. A is an element of the set that contains an element, which is the set that contains A. That's the best I can do, explaining it, verbally. The answer is false. Okay, because the only element of the right-hand side of the element of is by itself a set, and A is not a set, so that's why the answer is false. Okay.
So just because it's not a set, that's the rule.
Hmm?
The rule is that it's false because A is just by itself and not a set.
Correct. Yep. So the double, there's nothing. Okay, there's nothing. Okay, there's no such thing as a double bracket. It is a bracket within a bracket. So every time, and by the way, this is a brace, not a bracket. Bracket is the square one. Brace is the curved one. So this is a brace within a brace. So when you look at the right-hand side of the element line, this is a set that contains an element. The element itself is also a set that contains an element, which is A. If you look at lowercase a as a folder, it is in a folder, and then that folder in return is a part of another folder. Is that analogy working out okay?
What makes it true then?
Huh?
What would make it true?
There are several ways. If you remove one level of the braces, then it would have been true. Or if you add braces to the left-hand side, it would also make it true. Because in that case, the value that you're checking is a set that contains A, and you're checking whether that is an element of a set that contains a single element, which is the set with A in it. So in that case, it would also return true. Is that okay so far? Okay. And then question number 4 is true because a set is always its own subset. Okay, because it's basically asking, is every element on the left-hand side can also be found on the right-hand side? And in this case, you look and they go like, well, they're identical. So that means, yes, everything on the left-hand side can also be found on the right-hand side. So the answer is true for this one. All right, I'm just pausing to see if there are any questions. Okay. Number 5, here's the union. So in this case, choose the correct answer. ABC union with AB is ABC. The answer is yes. Okay, this is true because ABC can be found in at least one of the 2 sides of the union operator. Number 6. Now, these 3 are the fun questions because they say, okay, I'm not even telling you what is A and what is B. I'm asking you, is it always true regardless of what is A and B? Is it always false regarding, not telling you, not knowing what is A and B? Or it is sometimes true and sometimes false, depending on what is A and B. All right, so let's work this out, okay? So how do you approach a question like this? There are several ways, okay? The way I would do it, which doesn't mean this is the only way to do it, because some people can do it in a much more intuitive way. I'm kind of more mechanical, okay? I look at definitions, and then they go from the definition and explore out, okay? But some people are much more intuitive and to the point where they cannot explain how they get the answer. I know smart people like that, super smart, but they cannot explain anything. And they get super frustrated when they cannot do it. But in this case, it's mechanical. The first thing I need to know is the implication operator. So I need to ask the question, when is the implication operator true? Or I should say, when does the implication itself become true? When does it become false? Okay. So the truth table of the implication, you should know it by now, by heart. Okay. You should not need to look up a truth table because we have been using it quite a bit already, even just in the lectures. So in this case, I can look at this and go like, okay, I'm going to go for the this one first, okay? True regardless of how A and B are defined. So how can I make the implication true? If the left-hand side of the implication is always false, I'm done, okay? But in this case, I can make it true and I can make it false. Okay, fine. So in the case that the left-hand side is true, then I also need the right-hand side to be true in order for the implication to be true. The only time the implication is false is when the left-hand side is true, but the right-hand side is false. That sounds like less work. Let's try that, right? So I'll go ahead and say, can I create a scenario where A minus B is in fact the empty set, but it is not the case that A is a proper subset of B? So, well, that's not too difficult. Making A minus B to be the empty set, A and B just do not need to be, they don't have to share anything. And then on the right-hand side, if I want to say it is not the case that A is a subset of B, do you see how we can simplify that statement? Let me say that one more time. You guys, it will be kind of clear. It is not the case because we need this whole thing to be false. And now I state the actual expression that it is not the case that A is a proper subset of B. It's double negation. Go ahead. A is a proper subset of B. If A is a proper subset of B, then the right-hand side would be false. So I want to create a scenario where that is the case. A is a proper subset of B, and yet A minus B is an empty set. You go like, wait, hold on a second here. If A is a proper subset of B, it is automatic that A minus B is an empty set because everything in A is supposed to be in B. So that means, yes, I can make this implication false. So now the question is, can I make the implication true? Easy peasy, make the left-hand side false. That's easy, right? So how can I make it so that A minus B is not the empty set? A just has to, B is an empty set. A is not empty. Done. Yep.
So you're saying if, like, say A is 1, 2, 3, and B is 1, 2, 3, that would make the right side false because it's a subset?
That would make the right side true. Okay, so let's think about that case. Okay, I'm gonna write it out because I think it's harder for people to just listen to me, and kind of keep track of what I'm saying. So I need to go find my Joplin, which I thought I started earlier, but it's not there. Okay, give me a second here to start up Joplin. All right. Joplin. All right, so here's Joplin. And this is the right date. Okay, so there we go. All right, so we want A, okay, so I want to use equations here. We want A to be defined as 1, 2, 3, and B is the same way, right? There we go. And we want B to be defined exactly the same way, which is 1, 2, 3. Is that what your scenario is? Okay. So now we want to look at the expression. And unfortunately, this one, oh, this one does that too. Okay, very good. Except, it displays on this side and it doesn't give me the option of copy and paste. Fine. Now, copy and paste it here. All right. And then we want to evaluate, the left-hand side. And the left-hand side is just this part here, all the way up to here. Okay, so copy, paste. That pasted the entire thing, didn't it? Okay, give me a second. The $sign here, $sign here, and then we can get rid of a bunch of stuff. All right, that's better. So now what is that? What is this expression here? It is true, okay? So this is true. And I'm gonna use a 1 to represent true for this class. And now we need to look at the left-hand side. So the left-hand side is the issue because it is, it's a little bit tricky because we have a subset of B. All right, so you guys can focus on the right-hand side of Joplin. So now we need to look at this. Is that true or false? A is a subset of B is false. Because A and B are exactly the same, so it's not a proper subset of. But we have a negation operator on the outside, so it becomes not false, which is true. So in this case, this is also true. So we end up with true implies true, which is true. Are we doing okay so far with this? All right. So what is the answer then? So we went through a whole lot of derivation, and the answer is, it depends. All right. Yes,
So you can make the left side false and the right side true?
I can make the left side true and the right side false, and hence the implication is false. Yep. You have to remember the truth table of implication.
Has to be true and false.
Right. If the left-hand side is true, the right-hand side is false, then the implication itself is false. That's the only case that the implication is false.
What's the values that you put in to make it false? Like an empty set.
To make it false, so that means I need the left-hand side to be true and the right-hand side to be false. But in order for the left-hand side to be false, we need A to be an actual proper subset of B. So if you can make A an empty set and B anything other than an empty set, it will work. That would be a lazy person's answer because it's easy to write the empty set. Is that okay so far? No? Okay. I make A an empty set and B is anything other than an empty set. So that means there has to be something in B that is not in A. I don't even care what it is. Is that okay? So in that case, if A is an empty set, B is not an empty set, A is a proper subset of B is true. Not true is false. So I make this the right-hand side of the implication false. Yes, go ahead, sorry.
No, okay. Okay.
You good, okay? Okay. So we are taking the same thing, which is A being an empty set and B is anything other than empty set. A minus B equals to the empty set is true because if you're asking what is in an empty set that is not in blah, 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 something else, the answer is always nothing because you start off with nothing to begin with. So that means the equality on the left-hand side is true. Now we end up with true implies false, and that is the only case in the truth table of implication where the implication itself is false. Yes,
So is that symbol, the right-hand side, is that the proper subset symbol or the subset symbol?
that is the proper subset. Subset of has a bar under. So you can look at subset of kind of like less than or equal to, and then proper subset of is just less than. Yes. Well, I mean, it depends on the actual definition of difference and also subset of, proper subset of. So yes, you can look at it from the perspective of using quantifiers, but it doesn't really change the meaning of those operators. Any other questions? Okay. All right, so moving on to question number 7, which is of kind of the same nature, but this one is, okay, so we'll go ahead and work on this. A intersecting with B equals to A union with B implies A and B are the same. So the question is, well, one of the three, is it true regardless of how we define A and B? It depends on how we define A and B, or it's always false regardless of how we define A and B. So in this case, you can kind of think about what does it mean if A union B equals to A intersecting with B? What does that mean? Well, that means everything that is in both is exactly the same thing as everything that is in one or the other, right? Which also means there cannot be one thing in A that is not in B, because in that case, the union would not be the same as the intersection. It also means that there's nothing in B that is not in A for the same reason, because if there's something in B but not in A, then the union would not be the same thing as the intersection. So that means, yes, That means, the A and B must be the same. So this is just me using, the kind of the intuitive logic to figure this out. Question? Nope. Okay. So the answer is true regardless of how A and B are defined. Any questions about number 7? All right. Moving on to number 8. What is the value of the following expression? So same kind of deal. So with this one, kind of same thing. We look at this and go like, well, we'll try to figure this out. And personally, I lean on, depends on how A and B are defined, unless proven that it doesn't depend on it. So the first thing I want to ask is, can we make the left-hand side false? Plenty of way, right? Because, if B is an empty set, that automatically is false. And in those cases, the implication would be true. So the next question is, can I make the implication false? Which means I have to find a way so that A as a set is indeed an element of B. Well, that's pretty easy. We can make A an empty set and B is a set that contains just the empty set. That works, right? So now I need to look at the right-hand side and say, can I make that right-hand side false? If A is the empty set and B is an empty set that contains the empty set, then A is a subset of B is true, because the empty set is a subset of every set out there. But since we negate it, it becomes false. So I would be able to make the left-hand side true, the right-hand side false, but it's also very easy to make the left-hand side false, which means the implication is true. So now, it depends, okay? It depends on how A and B are defined. So in this case, it would be the second one, which is depends on how A and B are defined. Yes?
Is it possible to make an implication always false? Because it's so easy to disprove the next side.
Yes. So if the left-hand side always makes the right-hand side false, then you have an implication that is always false.
Okay.
But you do need the left-hand side to be always true to begin with. So you can start with something like the empty set is a subset of A, which is always true, assuming A is a set. And then you can make the right-hand side always false. You just have to come up with something, that is always false. Is that?
But couldn't you just make the left side like anything to make it false, which makes the implication true?
Well, you want the left-hand side to be always false, regardless how you define the variable. In this case, the set A and B. So you have to be careful. But when you say a subset, the empty set is a subset of A, that's always true, assuming A is a set. Yep. Number 7?
Well, I understand. My question is, so like, the reason it's not backwards, is because, like, if the left hand side is true, then the right is always true.
That's true. That's right. So in this case, I could have used a double-sided arrow here, which means if and only if, but I make the question a little bit easier, which is only one way. So all you need to do is to say, okay, to evaluate the 4 possible cases, and if the implication is always true, then we're good to go.
So basically, it's true, but there's no way that the right hand side is true without it.
That is correct. Yeah. There's no way to make the right-hand side true without also making the left-hand side true. Yeah. All right. So in terms of point values, this homework assignment is not super duper significant. So if you did not get a good score, it's not a big deal. But in the case of getting not such a great score out of this test, by itself is a good outcome, because it tells you that you may not be understanding all the concepts. And it is a prompt to go back to the material, try to read it again and try to gain a better understanding of the material. And remember, my office hour is right before class, okay? So try to make use of my office hour. I can also stay, after class for about half an hour to answer any questions. So those would be, good resources to make use of. All right, so I'm gonna score myself just in case I got a key wrong. Because I should be getting 8 out of 8 in this case, but I want to make sure. Am I getting all the points? 10 out of 10? Did it say anything? Yep, I got 10 out of 10. All right. All right. So we're now getting back to the originally scheduled program, which means we are talking about the injection, surjection, and bijection. So before we do that, let's go ahead and take a short break from all of these discussions. So I'm going to modify this one, to reflect today's road taking activity. You cannot see it yet, so don't, you cannot do anything about it yet. So let me go ahead and do this first. Today is 23 February 1st. And I want to use an access code. And union is the access code. I'll just write it on the whiteboard. Union. Which is kind of funny because I'm not a union rep anymore. I was, but not anymore. And then the time, it's 39 right now. This class, I'll give you guys all the way up to 1:20 p.m. You can do it in very, very slow motion. And then the question I'm going to change it to, so then give me a second here to change the question because I have to change everything to just true false. I am in class today. True false, update question, save and publish. And there we go. So go ahead and participate in the road taking activity. I'll give you guys some moments to do this as I set up for the lecture material. As per the suggestion of someone from my 310 class, I think I would try to use a QR code, but the problem with the QR code is I have to prepare that ahead of time. I don't think Canvas has built-in tools to deal with generating a QR code. Yeah. Question? No. Okay. So when somebody touched the hair, going, question? The professor's on the hair has a hair trigger. No pun intended either. All right. So it looks like, is everybody done with the road taking activity? Okay, all right. All right, so we're going to start with the description. So the first thing is, okay, if you do not have a function to begin with, don't bother to ask whether they are injective, surjective, or bijective. Okay, so these terms only apply when you start with a function. And last class, Monday, we talked about what makes a set a function. So in order to know whether something is a function or not, the first thing you need to do is to identify what is the domain, which is a set, what is the codomain, which is also a set. So the Cartesian product between the domain and the codomain would be one gigantic set, and your function as a set has to be a subset of the Cartesian product between the domain and the codomain. If your set is not a subset of the Cartesian product, there's no way it can be a function. Okay, so that's the first thing. The second thing is when you do look at the set, okay, which you think is a function, you should be able to map each element of the domain to one and only one element in the codomain. If that is not true, then it is also not a function. So are we okay with that concept, that we talked about on Monday? So we're clear on that one, okay? So now we can start with these properties. And the reason why we do these properties, okay, is to express what sorting means. Okay, so if you want to know the rationale of all of these mumbo jumbo discussion and all these abstraction and whatnot, the answer is we kind of need to be able to describe certain properties of certain functions in certain cases that we want to describe the correct outcome of an algorithm. In this case, we just want to describe the correct outcome of a sorting algorithm. Okay, so nobody would think that it is so difficult to actually describe what it means to have an array sorted. Because most of us think, well, that's pretty easy. You just have to say the element before the other one is less than or greater than, okay, depending on how you want to sort the array. So I'm changing the order of the lecture just a little bit because I want to show you why this is an issue. So it is at the end of module 289. So we're going to go to module 289, which talks about functions as sets, which is the lecture on Monday, but I did not actually go through that discussion. So we'll go ahead and use this discussion now. So the question is, okay, let's not read all this stuff here, okay? How would you describe, if you're the professor and you're asking your students to create an algorithm, to write an algorithm to do sorting, how would you describe the precondition versus the post condition of your program? In other words, what condition can you say about the array before the algorithm runs, and what condition do you expect after the algorithm runs? So I'll let you guys think about that just for a moment. The input, there's not a whole lot of requirements. Can the array contain duplicate items? I think it's reasonable. Okay, it all have to be of the same type, which you already expect in a strongly typed programming language like C++. Not a big deal. You can even make assumptions like the array has to have at least one element or something like that. Okay, all the usual basic stuff. The question is, how do you state the outcome? In other words, how do you make sure your student cannot come back to you and say, but you didn't tell me that I cannot do this, so you cannot take points away, huh? So how can you specify the outcome of sorting so that no student can come back to you and say, but you didn't say that and I cannot get all the points? So I'm going to give you a few examples that do not work, okay? And that leads us to the discussion of bijective function, which then leads to what is bijection? It's injective and surjective. Then we can explain what is injective and what is surjective. So I'm doing the rationale first, and then go back and talk about what those terms actually refer to. Okay, so using quantifiers, okay, we can do something simple. And okay, maybe I'll just go ahead and use Joplin to specify that. Okay, so assume A is the array and sorting is done in place. So that means all the elements are supposed to be staying in array A, and all you're doing is to move the values around within array A. The output is not a separate array, it is still in the same array. Is that okay? Okay. So the most intuitive way to look at this is, and I'll also use let n be the length of the array, so I don't use bar a bar all the time. Okay, so there we go. So we can do something like this. We can say for all, okay, for all I in okay, in a set where it is each element is x, and then x is in the funny looking Well, we can do the and thing, because it's the set of all natural numbers. And then we can just say and x is less than n. So what I have expressed up to this point is simply to say I is a valid index into the array. But in this case, I actually want to terminate one earlier. So I want to put a n-1 over here. And then the condition that I want to be true for every single possible I in that particular set is simply a bracket I has to be less than or equal to a bracket I plus 1. In other words, I want the array to be sorted in a non-decreasing order. So the question is, if this is the specification of the outcome, if this condition is true, you get all the points. Okay. So the question is, does that really describe sorting? The answer is no, because I can write a very simple program that will meet all of these requirements, and then you guys would go like, that's not sorting. So let me give you the code, and you guys can go like, ah, okay, that's interesting. All right, so I'm going to give you the code to do this. So we'll just say int I, and then the array is for I equals to 0. I is less than n, which is the length of the array, plus I. And then in the array, in the loop, I'm just going to say a bracket I gets 0. Done. So the outcome of this particular program is going to be this requirement, because every single element is going to become what? 0. Is 0 less than or equal to 0? Yes. But did this sort the array? It completely potentially destroyed what you were given with. So if somebody told me, this is my program, this is the solution of the sorting algorithm, and I think I deserve full points, because that is how you describe the proper outcome of the algorithm. I cannot argue, right? Because it does meet all the requirements. So what should I do next? Make a new assignment? How do I change the description?
Can you just say listen to avoid duplicates as well?
Sorry, say that one more time.
Can you just say not listen and just say listen?
That won't help.
So A sub I is listen, A sub I.
Okay, fine. Okay, let's see what that's gonna do. Okay, so we have a second version. Okay, so that's good. Okay, I like you guys just playing with this whole thing, and you're trying to come up with, okay, what if we do this and what if we do that? All right, so the suggestion is changing the less than or equal to a less than. So my solution, being the lazy person that I really am, I'm gonna do. So the answer to that is easy, because all I have to do is that. If there is a loophole, I will find it and exploit it. Yes,
So you have to make the set pre-sorting equal to the set after the sorting.
yes, but even with that one, there's still ways to not get the right answer. But I'll go ahead and explain that. Okay, so what Matthew is suggesting is something along this line. Okay, so the first thing I need is a way to express the original values of the array. Is that okay? So we need a notation for that, which is okay, because I can just add new notations. So I can now say, let k of I be the original value of a bracket I before the algorithm runs. Okay, so now we have a way to refer back to the old value in the entire array. So this gives me the vocabulary that is needed. Is that okay? All right. So now I can change the description here, and I still want it to be just less than or equal to, because I think having duplicate items should be okay. Okay, because if you give me an array like 5, 3, 3, 4, okay, it should be sorted to 3, 3, 4, 5, right? Yep.
So we need to do like X or like AI must be element, or just the whole. array
Something
should
like
be an
that,
element
yes.
of that.
Okay, so let's see how we can express that. So we can now, we will keep this, okay, because this seems to be useful, okay, because we want to keep this. But at the same time, we're gonna say, there's something else that we also want to specify. So what that other thing is now, saying for all I in X such that, oops, X such that X is a natural number and X is this time less than N itself. So like that. All right, so there's a conjunction here. So this I is only have a scope of here, and then this I here has a scope of here. Does everybody understand that the universal quantifier variable has its own scope? Once the scope ends, I can reuse the same quote-unquote variable in a different scope. Is that part okay? Or do you guys want me to use J or something else? That's okay? All right. All right, so for each possible variable or for each possible thing, I forgot to put a backslash in front of mathbb. There we go, looks better. So now I can specify, what is the requirement? So I can now say we should find that exists, okay, a J, and we want to specify where that J is coming from. Same thing, it is in the set of X is a natural number and X is less than N, okay, such that, okay, so I have to rematch the parentheses later on, and besides I can make this a little bit longer like that. Okay, so what I have at this point is I is a universally quantified variable. I basically goes through every single legal or possible index in the array. Is that part okay? Does everybody understand that I can go through every single legitimate index into array A? Because it starts with 0, because natural numbers start with 0. And at the same time, it has to be less than N, because the last element of an array has an index of the length of the array minus 1, because we start counting from 0. Same thing with J. J has the same constraints. So what about this, right? What are we looking at here? So we want A bracket I to equal to K of J. That's it. So what is this whole thing saying? The first part we kind of understand, and when the sorting algorithm is all done, we want every element in the array to be less than or equal to the one, that's on this next to it. Okay, that's a legitimate requirement. But the second part after this conjunction here is basically saying everything in the sorted array, we should be able to find that value before the array was sorted. That's basically what it's saying. But it's still problematic, okay? Because if you think about the array, okay, so I'm going to use, I think in this case, JavaScript notation is going to be useful. So the input, in this case, let input be 4337. Okay, and let output be 3477. So in this case, this outcome will still be qualified as a correct outcome. Because the question is, can I find 3 in one of the original values? Yes. Can I find 4 in one of the original values? Yes. Can I find 7? Yes. Can I find 7? Yes. So it still meets the requirement that is already stated here, but it really is not the correct outcome of a sorting algorithm. So we're still missing something because we need the same count of every single value. All right. So who would have imagined, stating or being able to express what sorting is about can be this difficult, right? So why do you think this is important, especially these days when OpenAI can already code? You can go to leetcode.com, okay, copy and paste one of those problems, paste it into ChatGPT from OpenAI, it will give you the Python code. So how does this relate to what AI can already do? Precision, okay, very good. Okay, so it has to do with how well can you describe the problem to be solved. Can you tell me the constraints of the input? What can I assume about the input of an algorithm? Can you very precisely describe the output? What qualifies as a correct output? That is the key issue. Because the AI may be able to go from the description of the output and go back and derive the algorithm to achieve that. But if you cannot express the correct outcome in a very precise way, then we have a problem. Do you see what I mean? So in the good old days, we only got manual solves, okay? And we got measuring sticks and whatnot, okay? And now we have a circular saw or we have a saw table saw. You know, the sawing part is easy. But are you cutting the wood to exactly the right dimension? That's a separate question because now you can just tell the robot, I need this wood to be cut to this dimension by this dimension here. The question is, can you express the specification of the output precisely so that the robot can do its own thing to make it happen? And I think this is one of the things that will make a difference in the age of AI when people apply for jobs. Because, you know, this is just me, you know, kind of looking forward a little bit. So in 2 years, if anyone is applying for a job for one of the big tech companies like Google, Pixar, and whatnot, they are no longer going to ask you questions like lead code. Instead, they will ask you to describe the proper output of something in a mathematical term. Because that is what is needed. What the AI needs is a very precise description of what the outcome is supposed to be. The rest, maybe the AI can do, but not the part about the specification of the code. But that's just me, you know, as a madman, you know, predicting, you know, what's going to happen in the future, which may or may not happen. Yep.
To clarify then, when the engineers at Google are designing search algorithms, they're writing it in this language to define what specifically is
Either this language or some other, you know, language, but it would be a specification language and not a programming language per se, because you're describing a condition that has to be met, you know, based on the output of the algorithm. You're no longer describing how to get it done. You're describing what needs to be done. And the what needs to be done needs to be described very precisely. Because if you don't describe it precisely, you can be missing things. Like, you know, what I did in this particular example, I went through a few iterations and I still cannot describe sorting. Yep.
Would you be able to say that Kj minus Ki is an instant and Kj union, I mean, no.
Well, but
Kj
this is an array. You cannot do an union with an array.
Oh, yeah.
Yep. You can create a impromptu set, okay, of all the elements or all the values in the array. You can create a set out of that. But the problem is not so much that we have all the same values. It has to do with they also have to be the same count of the values. And that means, you know, we need to be able to quote unquote map every value in the input to one and only one thing in the output. That is why bijection is useful. All right, so I'm just giving you this as an example of the rationale of why we need to talk about injection, bijection, injection and surjection, because when both of those are true, then we have bijection. And when bijection happens, then we can properly describe just what sorting actually means. Is that okay so far? Does everybody kind of understand, you know, from the higher level, you know, the rationale of doing all this stuff here? Okay, very good. All right, so we are looking at the time. Yeah, we still got about 18 minutes. All right, so I'm gonna get this one out, put this one back in. And we will go ahead and go to injection. All right. So in the injective function, which is also called an injection, so you don't want to use the word or the term injective unless you start with a function already. So in an injection, otherwise known as an injective function, each element of the domain maps to a unique element in the codomain. So let me highlight the most important word in this case, unique. So no two elements from domain should map to the same element in the codomain. That's basically what it's saying. So what we'll do is we're going to go through a few examples to illustrate what is injective and what is not injective before we get to the notation here. So let me go back to Joplin, and then we'll go ahead and use a few examples. Okay. So if I make F to be, okay, so we need the domain. Okay, this is the domain, X is the domain. So we want the domain to be 1, 2, 3, and then we also need to state the codomain, which is Y in this case. So we want to make Y ABC. And if F is mapping 1 to A, 2 to B, and then 3 to A again, F is a function, but it is not injective in this case. It's not injective because A1 is mapped to A, so it's 3. So that means 1 and 3 do not map to unique elements in the codomain. Are we good so far with this conclusion? Okay. So I should probably also state something here, which is again.
They don't.
They do not map to unique elements in the codomain. All right, so this is one example. And let me give you another example. So we can fix this by making 3 to map to C. And this time it is injective. Because in this case, each element in the domain maps to a unique element in the codomain. So we're good. Is that okay so far? So let me show you yet another example. So let's say the codomain contains an extra value D. It's okay. It's not a problem. Because the only requirement for injection or injective is each element in the domain maps to a unique element in the codomain. Is it okay for D in the codomain not to be mapped to from anything in the domain? Perfectly okay. Not a problem. Is that okay with the injection, the meaning of injection? Okay. Yep.
Would you be able to would you be able to also map 1 to D and it still be considered an injection, or since it's not a unique domain? Because of like
Say that one more time.
Okay. So what if in that last example you also had 1 combined with D?
All right. So what if 1 is mapping to D like that?
Oh yeah, and you still had 1 mapped to A as well. If you had both of those.
Oh, okay. So let's talk about this. In this case, F is not a function. So now we have to go back to the meaning of a function. Because in order for a set of 2 tuples, even if it is already a subset of the Cartesian product between the domain, which is X in this case, and the codomain, which is Y in this case, we still need every element from the domain to map to 1 and only 1 element in the codomain. And the last example did not make that true because 1 is mapped to not 1 and only 1, but it mapped to 2 elements in the codomain. So this is not even a function, and if you do not have a function to begin with, then the injective does not apply. Okay. So I have to kind of make sure that that is stated as well. So all we can conclude is this F is not a function. Yep. Question? Oh, okay. Are we good so far? All right. So now we switch back to the notes, okay, because now we get back to all those notations, okay? The notations are very important. Okay, if someone is thinking, oh man, this is like learning a new language, it is. It is a new language. Well, new to some of us, not new to some of us, okay, because it depends on your math background. Some of us may have exposure to these notations already, but this is the kind of language that can help us describe what the proper outcome of a program should be. Okay, and that's why it's important. So one way to say, some injection is to do something like this. Once again, this notation here means f is already confirmed to be a function. The domain is x, the codomain is y. So given that f is already a function like that, this is the extra requirement in order for f to be injected. So what it's saying is for every p in x, for every q in x, p does not equal to q, implies f of p does not equal to f of q. This is using the conventional way of using a function. You apply the function to a particular value in the domain, and it returns the corresponding value in the codomain. So is that understood? Is that notation okay? Because I'm switching back to the more conventional way of applying a function. You name the function, and then you put the parameters or argument, in this case, in parentheses. And then the whole thing returns the element in the codomain corresponding to, in this case, P and Q. Is that okay? All right, okay. So the other way to look at this is to use the notation that is a little bit more obscure. So this is the other way to describe it. So the other way to describe it is to look at this and you go like, I mean, it is natural for people to look at this and go like, I have no idea what this is. Okay. So the question is, what do you do when you say, I have never seen this before? So you have to do the recognition, okay? Recognizing components that you already understand and then work that way up to combine, all of these, multiple things is how we understand something that seemingly is something that we have not seen before. And there are two ways to do it. You can work your way from the outside in. You can also work your way from the inside out, or a combination thereof. In this case, I'm going to do a combination. So I'm going to start with a quantifier. The quantifier says for all q in y, blah, 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 okay? So what that means is the entire thing, the quantified expression can be true if and only if everything within the parentheses turn out to be true for every single element of y. If there's one single thing in y that fails that thing in the parentheses, then the entire expression is false. Is that okay? So now I know, what q is. Q is just a particular element in y that I'm focusing on, but I need to make sure that whatever expression is inside the parentheses turn out to be true, regardless of which element I choose to focus on in y. Are we good so far? So now our attention can turn into the parentheses here, or the expression inside the parentheses. It's a simple comparison. Blah, blah, blah. And the long thing is less than or equal to 1. All right. And what is less than or equal to 1? 0 is less than or equal to 1. 1 is less than or equal to 1. Okay. So what do we want to be less than or equal to 1? It's the cardinality thing. Bar, bar. Okay. Cardinality applies to a set. Okay. We're counting the number of things in a set. What set are we talking about? Braces. So this is the braces. This is a pair of braces that describe the membership of this set that we are constructing ad hoc. Okay, we are constructing this on the fly. What about the membership? What does each element look like? That's the job of the left-hand side of the vertical bar inside the brace. So every element is going to look like PQ as a two tuple. Well, we already have constrained what Q has to be. Q has to be an element of what? The quantifier itself is already constraining what Q can be. but it doesn't constrain what P can, which means it is, the two tuple just has to be something, and then the second item of the two tuple has to be an element of the codomain. Okay, what other constraints do we need? Well, PQ as a whole needs to be an element of F. That's it. In other words, give me all the two tuples in F such that Q is in Y. Pick any one element at a time and do this. Is that okay?
What is that?
So P can just be anything, as long as PQ, as long as you can put something into the position, the placeholder P, such that PQ together specifies a two tuple that is in F, that goes. All right, so I'm going to give you guys an example. We still got enough time, so an example would be helpful in this case. So let me switch back to Joplin. Okay, let me do this. Okay, I'm going to do a copy and paste. Switch to Joplin. And then we'll go ahead and take a look. Right, so Control V is pasting. There we go. And we want to. All right, so this is the original expression. What I want to do is to give you a specific X and a specific Y and a specific F. Okay, so we'll go ahead and pick up one of these examples here. Yeah, this one is a good one to choose. Okay, so I'm going to choose this one. So we'll go ahead and I will go ahead and copy and paste this. And once again, you just have to focus on the right-hand side, and I will continue to do some editing on the left-hand side. So we know what X is, we know what Y is, we know what F is. And I'm going to erase that part. Yep.
Is this an alternative way to check, or is it additional way to check?
This is a way to check. Okay, so that's a good question. The question is this the only way to check whether a function is injective or not? This is just one way to express it.
And then the other way is,
The other way is to describe it. Every element in the domain maps to a unique element in the codomain, or the other notation. But in your test, I can throw you something like this. It is using the operators that individually have been introduced in class, just not combined the way it is in the test. Okay, I can almost guarantee you that there will be questions like that. That is kind of my trademark. That some people absolutely do not like. All right. So now we have this example here, and then I'll focus on one particular Q. Okay, so instead of saying for all Q, I'll give you exactly which Q we are talking about here. So I'm going to say, okay, I'm going to erase the whole thing. I'm going to rewrite the entire thing. So let's say Q equals to, let me see, which one is a good one to do? C, okay, so let's say Q equals to C. Then the question is, what is, and then now I have to copy the whole thing, which is the set where we have PQ, P comma Q, such that P comma Q is an element of F. All right, okay. That's the question, okay? I'm giving you what X is, I'm giving you what Y is, I'm giving you what F is. So I want you to construct this particular set impromptu, knowing what Q is possible. So what is the result of this question? And I'll give it even a variable name so I can easily refer to it. So XY is already used, we're going to say W, okay? So what is the answer? What is W? So this is basically about understanding the notation. The notations have all been introduced. The question is, can you apply what you already understand about the notations and combine all those notations in this specific way to answer the question?
that's the empty set.
It is the empty set. Very good. Okay, so in this case, it is the empty set. Because when you look at function f as a set, and I'm asking, give me all the two tuples that has the second item in a two tuple being C. 1A, no. 2B, no. 3A, no. So that's why the answer is an empty set. All right, so yeah, go ahead.
We didn't really care about B because we're just asking for the elements of Q.
That is correct, because P is not a constraint. There's nothing about P that is a constraint, but because we know the value of Q already, that is our only constraint, which means P can be anything. This, okay, remember what this one says is basically saying for every PQ in F such that your Q equals to C, that element belongs to W.
But P still has to be a unique like domain. to make
No,
it a function.
P can be anything. P can match anything. So, okay, so that's a good question because I think the second example is going to fix this problem. It's going to answer that problem, answer that question. So let me do it like this. And we'll ask what is W again. But this time I'm going to make Q, let's see, A. There we go. All right, so this is the second question. This is the first, this is the second. So in this case, I have the constraint of Q equals to A. So I'm asking, give me all the tuples, okay, in F, such that the second value of the two tuples is A. So in this case, there are two of them, because in this case, we have what? 1A, as a two tuple meets that requirement, 1A. And we also have 3A meeting the same requirement. Is that okay?
So there's two.
Yeah, because it is the same notation that we use to express the set of all even numbers. Yep.
So if, so with the first item, say 2B was AB, it wouldn't matter because the second, that's the second item in that table is a B. Say that P is A. And
P is-
Q is B, it wouldn't matter, right? It wouldn't go into W.
Okay, so PQ is already constrained by PQ together has to be an element of that. So that means we only have these three to be valued as the potential two people that can be contained in this particular
My
set.
question is, if we change one for an example, like if it was 1A, AB, 3A, B wouldn't fall under that constraint, or AB wouldn't fall under that constraint because.
Correct, because Q is already known to be A. So when you try out 2B, it does not meet the requirement that the second item has to be A. But AB as a two tuple is not in F because it cannot be. Because AB as a two tuple is not an element of the Cartesian product between 1, 2, 3 and ABC.
So if we go back to the original form, so Q is element of Y, not just A or C, then we can report all three pairs.
So what you need to do in this case is if you want to evaluate the for all, then we are missing one application. So the application that we are forgetting here is what the Q equals to B. So if Q equals to B, then we have 2B being the only element of that set. So so these three, okay, let me put here. Okay, so these three here, this is one. This is the second one. Oops. And this is the third one. I keep pressing the key to save the file, but it wants me to pay for the file storage. So when you look at these three, that's what the for all is trying to do. The for all is basically saying, for all elements in Y, how many elements do we have? That are in Y. There are three. So we are asking, let's consider C as the element that we have chosen from the codomain. What would be that case? And what would be the cardinality? It would have been 0. So it would have failed us, it would have satisfied the test of being less than or equal to 1. So we're good with that. But that's not the only element in the codomain. We have A also being in the codomain. So now we have to evaluate A also. In the case that Q equals to A, because Q is just a placeholder, then W would have been 1A, which means the cardinality would have been 2. 2 is not less than or equal to 1, so we would have failed that condition. The for all thing would have failed, because in order for the for all itself to be true, this condition here, the set having 0 or 1 element has to be true for regardless of what we choose to look at in the code. Is that okay? All right, so remind me next time, I know we're running out of time. So next time I can give you the JavaScript code corresponding to this, if that helps. I mean, I'm not sure whether that's going to help, because in some cases it can make it worse, because now you have to learn yet another language, which is JavaScript. All right. Yep. Have a nice weekend, indeed.
So Professor.
Yep.
In this example, for all we fail, you said,